Hello there. This lecture is all about empirical probability. And empirical is kind of a fancy way for being able to prove something based on data. So with empirical probability, you're using data that you've collected in the past to make predictions about the future and to just understand the data in general and how likely certain outcomes were or how many people or items met certain criteria. Now, to make accurate predictions about the future, it's really important that you have representative data. So you're going to see some examples where we're looking at data that was collected on a particular day in the past, and they're going to use that to make predictions about the future. But if that data collection isn't an accurate representation of what you could expect to see for the whole year or for the time period that you're trying to make predictions for, your predictions aren't going to be very good. For example, if you were trying to make predictions about the number of purchases per transaction at a retail store, probably wouldn't want to just collect data during December when people are buying presents for Christmas. That's not going to be an accurate representation of the whole year, how many different types of items are in each transaction. But if you're just trying to make predictions for this Christmas based on last Christmas, then just collecting that data last December would be fine. So again, you want to make sure your data large sample size, representative of what you're trying to predict in the future. Also note that we're focusing now on just discrete data. So data that is fixed to whole numbers if it's numeric. So like number of customers, number of purchases, or data that's just categorical in nature. It's nominal or ordinal data. It's not numeric in any sort of way. So it's just fixed categories like payment method, delivery method, department, things like that. Also, for the first time, you're going to see that I'm going to specifically ask you to try some of the problems in the video. So I'm going to have you pause the video and try the problems that are in gold. After I demonstrate how to figure out the probability, I want you to try it yourself. Because even with Excel, you need to understand the logic and the math behind these probabilities to be able to compute the probabilities. So doing that practice is really going to pay off, not just for your lecture quiz, but also for your Excel practice assignment, and then finally for your technical report.
So in this lecture, I'm going to start by introducing you to the concept of empirical probability and the terms associated with empirical probability so that what we talk about in the example problems will make sense. Then I'm just going to go over some general probability rules and a recap of relative frequency, which is just the percentage of any specific outcome in your data set. And you were introduced to that in the frequency distributions lecture quite a while ago. Then we're going to spend quite a bit of time looking at all these different probability rules associated with different types of outcomes that you would be interested in examining. And then I'll summarize all those rules at the end with a summary of the formulas. And those summaries will really help you when you go to do your technical report and you need something to look back on. So this lecture does not focus on classical probability, which is another way to examine discrete probability. And classical probability it really is in a situation that requires knowing the total possible outcomes. So every possible event that can occur, you have to have collectively exhaustive knowledge about what could happen. So for instance, the events of rolling a 1, 2, 3, or 5, or 6 on a 6-sided dice are collectively exhaustive, right? We know if we roll a 6-sided dice, one of these outcomes is going to occur. We're going to get a 1, 2, 3, 4, 5, or 6. Classical probability also requires that each event has an equal likelihood of occurring. So with the dice example, you have a 1 in 6 chance of getting a 1 if you roll a 6-sided dice. You have a 1 in 6 chance of getting a 2, a 3, a 4, a 5, or a 6. Now, while classical probability is really useful for things like gambling, empirical probability is more applicable to business situations. Because for most business-related data, each outcome is not equally likely. We rely on a sample of observations to predict or estimate the probabilities of events. It's not as predictable as what would happen in a classical probability situation. So for example, let's say that a hospital administrator wants to know the probability of each arrival method for any given patient to help them determine staffing needs for helicopter pilots or ambulance drivers or paramedics versus front desk clerks who check walk-ins in. Or maybe the hospital wants to look at the proportion of arrival methods based on condition to see if patients are overusing the ambulances or the medical evacuation. In this case, classical probability is no help because the probability of each arrival method and condition is not equal. Although you can map the sample space for any given patient, which just really maps out every event that could possibly occur, Which event occurs is not due to chance, but to a variety of factors like money or the availability of transportation or age or insurance. So, empirical probability could be used to count the arrival method and condition over a period of time, and then that could be used to estimate the probability of conditions and arrival methods in the future. So, that would be, again, empirical probability, and that's why we're just going to focus on that in this lecture, because classical probability doesn't really apply to most situations in business. If you want to be really good at blackjack, learn about classical probability, but that's not the point of this class. Now, empirical probability has some requirements. It requires matched conditions that are representative of the outcome or time period of interest, and I mentioned that earlier. Also, in addition to having the matched conditions, you should have as large number of observations as possible to have an accurate prediction of the probability of an event. So you need to think about if you're collecting data on patient arrival methods and condition, would the 197 patients who arrived today be representative of all patients in the future? Probably should collect data over a longer period than just a day. And think about it. What if you collect your data during an extreme circumstance? What if you collect your data on New Year's Eve? Well, there's a lot more alcohol flowing, there's probably more injuries, and people are probably less able to drive to the hospital. So you would underestimate the number of walk-ins that you should have on any other day. Also, again, with empirical probability, you want to try to collect as much data as humanly possible. So maybe look at an entire year or randomly selected days out of the year instead of just one day. But this is not always possible due to time constraints and limited access, so you just kind of have to make the best with what you've got while considering how well your predictions are going to actually predict the future based on how strong a data collection you actually had. So before we actually jump into actually looking at different types of probability based on empirical data, we need to fully understand some terms that are going to be used in this lecture. Some of these might be review, but some of them are new, so make sure that you understand these before you move on. So the term variable is just a broad category that encompasses a variety of events within a category. So it's kind of a broad categorization, and then there's specific things within that variable, specific types of outcomes or events related to that variable. So for instance, hospital arrival method and condition would be two variables. And then you would have an event or a specific outcome or observation for that variable. So for hospital arrival method, you could arrive in an ambulance or a helicopter or be brought in by a prison guard. For the condition, the specific events that could happen for that variable would be being in critical condition or in good condition or stable condition. Also thinking about when you're looking at different outcomes that could possibly occur, looking at mutually exclusive events. So these are events that could not co-occur. So two things that can't happen at the same time. So for instance, a patient could arrive in an ambulance or be a walk-in, but they're not going to do both. So arrival method is a mutually exclusive event. You show up in one way, you're not going to show up in another way. Non-exclusive events are just the opposite. It's events that could technically co-occur. And typically when we look at non-exclusive events, they're events that are based on different variables. Now, if you're looking at more than one occurrence, you could say maybe somebody could arrive in an ambulance and then the next person could arrive in any arrival method. But typically we're just looking at one outcome at a time. So for instance, you could arrive in an ambulance and or be in critical condition, right? Now we're looking at two variables. So those two things could co-occur. Maybe they don't, but they could. Dependent events are when the first event has an impact on the probability of the second event. So these things are definitely co-occurring. So non-exclusive, they could co-occur, but when we talk about dependent events, they do co-occur. So you could arrive in an ambulance and be in critical condition. So you could look at how many people out of everybody in the sample arrived in an ambulance and were in critical condition. Or you could narrow it even more and say when someone's in critical condition, how likely is it they would arrive in an ambulance? So in that case, you would just be looking at people in critical condition. It's like the prerequisite, and then you would see the probability or the proportion of patients that arrived in an ambulance when they were in critical condition. And then finally, independent events, that's when you just have one variable. And that's really more related to when I was talking about non-exclusive events earlier, where there's two different outcomes being measured. This is when the first event has no impact on the probability of the second event. So for most of these examples, we're just talking about one patient, right? They could be in an ambulance or walk-in. They could be in an ambulance and or critical condition. They could be in an ambulance when they're in critical condition. But for this, we would look at multiple patients. So for instance, the condition or method of arrival for the first person observed has no impact on the condition or method of arrival for the second person observed. So subsequent data points are not dependent upon previous data points. So as you learned about in the previous lecture, probability is just a numerical value that tells you how likely a specific event is. So the likelihood of a given outcome, or you can talk about it in terms of how much of the sample represented this specific outcome. Remember, to get the p-value, or the probability or proportion, you just take the percent, divide by 100, and to switch it to a percentage from a p-value, you just multiply by 100. When you're dividing by 100, you can just scoot the decimal place 2 places to the left. When you're multiplying by 100, you can just scoot the decimal place 2 places to the right. Also remember that the probability for one event is never going to be negative. It's never going to be less than 0. It's also never going to be greater than 1. Because if you think about it in terms of percentages, if it's 100%, right, 1 times 100 to give you 100%, that is an outcome that is certain. It's likely, or it's absolutely going to happen. So you can't have more than 100% chance of something. Also, when people say they're giving their 110%, it drives me nuts because all you can give is 100%. That's the maximum. That's the top. All right. Also think about in terms of percentages, 0% means that the outcome will certainly not happen, right? So think about it. You can't have a negative probability. 0% is as low as it gets. You can't have an even less chance of something than never having it happen, if that makes sense. So any probability between 0 and 1, or any percentage between 0 and 100 represents the uncertainty. We're not certain. The closer to 1, the more certain we are, and the closer to 0, the less certain we are. But if it is 0, we're certain it's not going to happen. So just to demonstrate these probability rules, let's say that in one day you collect data on the condition of patients arriving to the hospital. So if you have 197 patients observed today, you could see that 98 out of 197 were in good condition. So that gives you a probability of 0.497. And 50 out of 197 were in fair condition, probability of 0.254, or proportion of 0.254, however you want to say it. Serious condition, 35 out of 197. That gives you a p-value of 0.178, and then only 14 out of 197 were in critical condition, and that gives you a p-value of 0.071. So based on this, we know that if we turn it into percentages, 49.7% of patients today arrived in good condition. And if we think that this day represents the future, we would say that on any given day, we could expect about 49.7% of patients to be in good condition. So let's get rid of this marking. So notice here, 0.497 plus 0.254 plus 0.178 plus 0.071. So basically adding all of these probabilities together, you get 1. Because there is a 100% chance that any given person you select from the sample would be in good, fair, serious, or critical condition. And conversely, 100% of the sample was in good, fair, serious, or critical condition. This represents all the possible events that are associated with this variable, all the possible conditions that you could have had. Now, something called the complement rule is basically the probability that the outcomes are not part of the event. So let me show you what that looks like. So if you think about it, there's a 100% chance that someone in your sample is good, fair, serious, or critical condition. So to figure out the probability that they're not in a specific condition, you would take 1, right, the probability of any outcome, and subtract the probability of the event that you are not interested in, right, will not happen. Or if you're doing percentages, you could take 100 minus the percent associated with the events you're not interested in. So if you think about it, you could also take the probability or percent that any outcome will happen, 1 or 100, right? And subtract the probability or percent that the event will not, or the event will happen. And that tells you the probability that it will not happen. So examples help because that seems very strange. But if we look at this, the probability that a patient was not in good condition. Remember, the probability that a patient was in good condition was 0.497. So if you want to know the probability that they're not in good condition, You could take 1, the probability of any condition, minus 0.497, the probability of good condition, and you know that there's a probability of 0.503 that that patient is not in good condition. Or you know that 50.3% of patients were not in good condition. You could, if you had all the data available, get this number right here, this 0.503, by adding the 0.254 for fair and the 0.178 for serious and the 0.071 for critical. And guess what? You still get 0.503. So again, the complement rule is if you know the probability that an event will happen, then the probability that the event will not happen is 1 minus that probability. So let's start with a really simple example where we're just looking at relative frequency for a single variable. So you can see here that this data represents observations of emergency room arrivals at St. Rose in a 24-hour period. And you'll also see that this first column here represents all the different methods of arrival, and then how many patients out of a total of 197 had that method of arrival. Then in this column, you'll also see the probability or the relative frequency. Same thing. This should not be foreign to you. You saw something very similar to this in your lecture on frequency distribution tables, but we're going to review it again anyway. So first thing I want to point out, notice again that the P, the probability, for all events is 1 because every event observed method of arrival in the sample is included in the table. Also, you'll see, again, there's 197 patients total, so the denominator for all of these p-values is 197, total number of observations. You'll also see that the numerator for all of these, and let's change our color here, probabilities, is the number of observations of interest. So for instance, how many walk-ins? 132 out of a total of 197. So based on this table, we can answer these questions pretty easily. The proportion of patients that arrived in a helicopter comes straight from the table, 0.01. And the proportion that did not arrive in a helicopter, you could use the complement rule to find that out. So you would take 1, the probability of any event, subtracted by the probability of the event we're not interested in, helicopter, you get 0.99. You could also add walk-in, ambulance, and prison guard and get the same number. So now I want you to pause the video and take a second to figure out the probability of a walk-in and the probability or proportion, however you want to think about it, of a not walk-in. All right, so hopefully you tried that on your own. So we'll take a look at the table. Walk-in is right here, and the probability associated with a walk-in is 0.67. If we want to figure out the probability that they're not going to walk in or that they're coming in an ambulance, helicopter, or from a prison guard, you could just do 1 minus 0.67 and you get 0.33. And again, you could just add these to get that same value. So now I'm going to show you some examples using these different probability rules when we have independent events. So events that don't necessarily rely on one another. So when you're looking at a single variable, like method of arrival, with outcomes that cannot overlap, and the word or is involved, then you know you're probably looking at the addition rule for individual outcomes. So data that would be used for the addition rule for individual outcomes is usually mutually exclusive events where there's no overlap because a single patient cannot arrive in multiple ways. So here's that table again, and you'll see here that usually, in most cases, empirical probability is used to anticipate events, like predicting the probability or likelihood of future outcomes. So based on this table, you could say that based on the past 24 hours, the estimated probability that the next patient arriving in a helicopter or ambulance would be 0.32, right? Or 32% chance that the next patient would arrive in a helicopter or ambulance based on this data. And I got that from taking helicopter, ambulance. And you could do this 2 ways. You could do the sum of the probabilities for each event. So you could do helicopter plus ambulance. So that 0.01 plus 0.31 equals 0.32. Or you could add the frequency in the cells of interest, ambulance, helicopter, 2 plus 61, and divide it by the total number of observations, 197. Either way, you get 0.32. Now, of course, there's several factors that may impede the accuracy of this estimate, like the limited time of observation. Maybe this was on a Monday and there's more drunk driving and need for life flights on the weekend, so it wouldn't be a good estimate of that. If you were simply interested in the 24-hour period of data collection and you did not have the goal of using this observation to predict future events, then instead of saying, the probability that the next person will arrive this way, you would say the proportion of arrivals by helicopter or ambulance was 0.32, or 32% of arrivals were via helicopter or ambulance. So if you're trying to make predictions, you would say there's this much of a chance of this happening based on the data. And with the same numbers, if you're just talking about what happened that day, you would say that this many or that proportion or percentage of arrivals were that method. Just to remind you of the complement rule, if you wanted to know the probability that the next arrival would not be helicopter or ambulance, or the percentage of patients that day that were not helicopter or ambulance, you would use the complement rule. You could just take 1 minus 0.32, right? 1 minus the probability of helicopter or ambulance and get 0.68. Or you could add walk-in plus ambulance here, add those two. Or you could take 132 plus 2 divided by 197. So now I want you to pause this video and take a moment to try this on your own. So try to figure out what's the probability that the next person will be a walk-in or a prison guard based on this data, and what's the probability that the next person that comes will be a walk-in or not walk-in or prison guard based on this data. Okay, so hopefully you gave that a try. It'll help you practice than just watching me do it. So here we go, P, walk-in or prison guard. So we're going to add the probabilities first. So the probability of a walk-in is 0.67, and the probability prison guard is 0.01. Add those together, and you get that 0.68. You could use the other version of the formula as well, and you could say, okay, so the sum of cells of interest, well, 132 were walk-in, plus 2 that came in with a prison guard, divided by 197, and you end up with, again, 0.68, or 68% of patients arrived as a walk-in or with a prison guard. Then you could use the complement rule to figure out not walk-in or prison guard. 1 minus 0.68 equals 0.32. So now we're working with a situation where we don't have access to raw data, but we have some probability or percentage values to work with. So in this case, we're going to have to focus on this version of the formula because we don't have any cells of interest or frequencies to account for. So this data is actually looking at data based on institutional research collected at Nevada State College, suggesting that about 23.4% of students are freshmen, 20.5% of students are sophomores, 25.3% are juniors, and 30.8%, or the majority, are seniors. So if you were asked what percentage of NSC students are upper class, juniors or seniors, right? They can meet either criteria and be counted as upper class. You would just add the probabilities for juniors and seniors together. So you would add this 25.3 to this 30.8, and you would know that 56.1% of NSC students are juniors or seniors. Now for the next one, what if I asked you what percentage of NSC students are underclass, not juniors or seniors? Take a second and try to figure it out before you watch me do it. Okay, so hopefully you pause the video and try it on your own. This one's not too complex. There's two ways you could get it. One way is the complement rule. So since we're working with percentages, we're not going to use 1, we're going to use 100. So 100%, all the students minus the percentage who are upper class, who are juniors or seniors, right? So 56.1, and you end up with 43.9% are not juniors or seniors, or in other words, are freshmen or sophomores. You could also take the percentage of freshmen, 23.4, right, from here, plus the percentage of sophomores, 20.5 from here, and guess what? You get 43.9%. So 56.1% of students are upper class, juniors or seniors, and 43.9% of students are not juniors or seniors or underclassmen. So now let's move on to the multiplication rule for independent events. We're going to start with raw data and then look at a story problem. So when you're looking at a single variable, like method of arrival, for instance, with outcomes that cannot overlap, and the word and is involved, you're probably looking at the multiplication rule for independent events. And typically, the independent events are events that happen in sequence. It's not something that's all going to happen at the same time. So again, you use it when you're looking for the probability of something and something else, two independent events. We have a single variable, so x is one level of the variable, y is the other level of the variable. So like ambulance and helicopter, or if you're looking at condition, like good and critical condition, two different types of condition. And we have mutually exclusive outcomes, meaning that if somebody is in critical condition, they cannot be in good condition. If somebody arrives in a helicopter, they can't also arrive in an ambulance. Now keep in mind, you'll see that you can do this for as many events as you have. So if you have 5 independent events, you're just going to be multiplying 5 probabilities. In this particular example, I think we're just going to be looking at 2 separate events happening, but you'll see there's 2 versions of the formula. This one is best when you're working with raw data, but basically by taking the number of cells in the cells of interest and dividing by total observations, you're getting probabilities. So you're essentially doing the same thing with this formula as you are with this formula. You just figure out the probability and then you multiply all those probabilities for each event together. So let's take a look at this table again. We've got the method of arrival. We've got our frequencies right here. So this would be like the sums of the cells of interest, depending on what we're looking at. And then we've got our probabilities right here based on those frequencies and the fact that there's 197 total arrivals. So if you were asked, if you select 2 patients at random, what's the probability that both would have arrived in an ambulance? So our first event is arriving in an ambulance, and our second event is arriving in an ambulance. Well, since we already have the probabilities calculated, right? We've already done this math here. We've already got our total number in ambulance divided by the total number of observations to get this 0.31. You can just take the probability of arriving in an ambulance, 0.31, times the probability of arriving in an ambulance, 0.31, and you get 0.096. Or it's there's a 9.6% chance that any given 2 patients both arrived in an ambulance. Now these are mutually exclusive because whatever happens with this first patient has no impact on what happens with this second patient. These events are not dependent upon each other. So now I want you to give it a try on your own, looking at these 2 gold problems. Now remember, you just multiply however many events you have, right? So we're going to be focusing on these formulas and give it a shot looking at the probability that the next 3 patients would arrive in the ambulance, and then the probability that the next 3 patients would walk in. All right, so because we already have this math done for us in the table, we're going to focus on this version of the formula. So the probability of the next 3 patients arriving in an ambulance would be, well, we know that the probability of 1 arriving in an ambulance is 0.31. So we take 0.31 and cube it basically, right? Because there's 3 we're looking at equals 0.31 times 0.31 times 0.31, and we end up with 0.03. Or there's a 3% chance, based on this sample, that the next 3 patients will arrive in an ambulance. So pretty unlikely to happen. It's likely to happen for any single patient, but not 3 in a row. All right, probability of the next 3 patients walking in. So that would be this probability now, 0.67 times 0.67 times 0.67. Now keep in mind these examples show you for the same exact type method, but you could do it for 3 different methods. Like if you wanted to say that the next patient would be in an ambulance, or I mean among the next 3 patients, one would be in an ambulance, one would be a walk-in, one would be a helicopter, you could just multiply those together. Here we go. So 0.67 cubed, right, because we're multiplying it by itself 3 times, is going to be 0.301. Or there's a 30.1% chance, based on the sample, that the next 3 patients are going to be walk-ins. Notice this is much more likely than this, because the probability of showing up in an ambulance in general is lower than the probability of being a walk-in in general. But notice that every time you multiply, it gets smaller and smaller and smaller, because now you're getting into more unlikely outcomes of more people showing up in that method of arrival. So now we're going to look at a scenario using the multiplication rule for independent events where you don't have access to the raw data. So the only version of the formula that we're going to be seeing here is this version where we're working with probabilities or percentages. Now be prepared for word problems, and be prepared if you see percentages, you can convert them into P by using the percentage divided by 100 equals P to do your math. So based on past experience, you know there's a 3% chance that a terminated employee will try to sue the company for wrongful termination. Or in other words, your past research, your past data suggests that 3% of terminated employees try to sue the company for wrongful termination. You also know, based on past data collected, that there's a 55% chance, or 55% of employees will be terminated. So if you just terminated 2 employees, you want to know how likely or the probability that both will sue. So you've got sue and sue situation, right? Multiplication rule of independent events. So if we look at this, we know there's a 3% chance that a terminated employee will sue. If we're looking at 2 employees, we just take that 0.03 and square it. So 0.03 times 0.03, 0.001. Or if we turn this back into a percent by scooting the decimal place 2 places to the right, there's a 0.1% chance that both of those employees will try to sue for wrongful termination. Now I want you to try the next one. So suppose you just terminated 3 employees. What is the probability, the estimated probability that all 3 will sue? You can expect it to be lower than this, because now we're looking at an even more unlikely outcome. More things have to happen for it to be the case. Okay, so hopefully you tried this on your own. You're going to have 0.03 cubed, which is the same as saying 0.03 times 0.03 times another 0.03. And you end up with 0.0000027, or a 0.00, we scoot this 2 places over, 3% chance that those 3 terminated employees will sue. Keep in mind with rounding, you want to round until you at least get to some numbers to work with here. When you do p-values, if you're going to turn it into percent, at least have 2 numbers that aren't 0 present so you can round it appropriately for the percentages. So now let's take a look at a problem that's definitely relevant for you, regardless of your business experience. So let's say that a student, definitely not you because you're watching this right now, but let's say a student does not have time to watch the lecture to prepare for the lecture quiz, and they just wing it. They just complete the lecture quiz by randomly guessing on all 4 questions. And let's say that for this particular lecture quiz, each question only has 4 choices, A, B, C, or D, and there's only 1 correct answer for each. So if we're talking about the P of the first event, or the probability of getting 1 correct, that would be a 1 in 4 chance if we were just looking at one problem at a time. So 25% chance that you would get it correct by chance if you're just looking at one problem. But how likely would it be for you to get more than 1 correct, right? So if we're looking at the probability of getting just 1 correct, it's the same as the probability of getting it correct if you just have 1 problem. So it'd be 0.25. But if we're still looking at those 4 questions and we want to know how likely, if you just randomly guessed, would it be that you would get 2 correct? Well, now you're going to take the first event, correctness, 0.25, times the second event, 0.25, and you would get 0.0625, or a 6.25% chance that if you randomly guessed, you'd get a 50% on the quiz, or 2 correct. Go ahead and take a look at 3 and 4 and try it on your own. All right, So if we want to know the probability of getting 3 correct, you're going to take that 0.25, the probability of getting 1 correct, and cube it. So you'd have 0.25 times 0.25 times 0.25. So that will give you 0.0156, or a 1.56% chance that you would get 3 correct. Now let's see how likely it would be if you randomly guessed to get a perfect score. So now we're going to take 0.25, multiply it by itself 4 times. So 0.25 times 0.25. So many 0.25s times 0.25. And we get 0.0039, or 0.39% chance that you would get a perfect score. So the moral of the story is, don't randomly guess. Now, up until now, we've kept it pretty simple, and I've really focused on the probability of a single event. However, in the business world, situations are rarely this simple. Oftentimes, they involve 2 or more events that intersect with one another. For example, maybe a hospital wants to know how method of arrival to the ER and medical condition intersect, right? So if you have 2 variables that occur simultaneously and you see the word or, you're probably dealing with the addition rule for 2 non-exclusive events. So if we take a look at this data, now we're looking at 2 events. We're looking at the method of arrival here, and we're looking at the condition right here. So what if we need to know the probability that the next ER patient will come in an ambulance or be in good condition? So we've got good here, ambulance here, and here's where those 2 things intersect. So basically, we're looking for everything in this Venn diagram, right? So this intersection represents this right here, but we're not saying that they come in an ambulance and in good condition, right? That would be just this. We're saying they can either be in good condition or they can show up in an ambulance. So that's representing all of this here. Now, the most important thing is that when we're doing this, we don't want to double count this intersection, right? We don't want to double count this 7. We don't want to count that 7 twice. So you'll see the formula I'm using is the number of events in the cells of interest divided by total observations. There's an alternate version of the formula where you will use the marginal frequencies and then divide by the total number. But if you do that, you're going to double count, right? You're going to double count that 7 because that 7's included here and that 7's included here. So I suggest when you have a problem that looks like this, you just kind of highlight or look at all of the relevant cells for both conditions, add those together, and then you divide. So you'll see that right here, right? So we've got the 90 plus the 7 plus the 1 plus the 30 plus the 20. Oh, sorry, plus the 20, get out of here, 30, plus the 22, plus the 12, right? So those highlighted cells. And when you do that, you're not inclined to count this 7 2 times. You're not inclined to double count the intersection. So you add those together, you get 152 divided by 197, and you get 0.772 is the probability that the next ER patient will come in an ambulance or be in good condition. Again, either one of those conditions can be met, or both. So now I want you to try this on your own. Make sure you don't double count the intersection of the 2 events. Don't bother using the marginal frequencies like they show in the textbook because you'll double count. And give this a try. So pause the video and try it on your own. Okay. So what if we need to know the probability that the next ER patient will arrive in a helicopter or be in critical condition? Or in other words, we want to know what proportion of patients from our data set arrived in a helicopter or were in critical condition. And of course, we're using that to make those predictions. So if we look at this, we're looking at helicopter or critical. So here's our critical zone. Don't count these marginal frequencies or totals. helicopters right here. So if we add all these together, I'm going to ignore the zeros. We've got 12 plus 2 divided by the total number of observations, right, 197. And we end up with 0.0711, or a 7.11% chance that the next patient will arrive in a helicopter or be in critical condition based on this data. Well, what if we want to know the probability that the next ER patient will not arrive in a helicopter or be in critical condition? Well, what we could do, instead of going, okay, let's add up all the things that are not serious and critical and divide, that's no fun. Let's use the complement rule. So we'll take 1 minus the probability that they will be critical or in a helicopter, and you end up with 0.9289, or a 92.89% chance that the next patient will not be in critical condition or arrive in a helicopter. Again, these are predictions, estimates based on limited information, but it's better than just randomly guessing, right? If you have past data to make predictions with, it's a lot better, even if it's not 100% accurate. So now let's take a look at an example of the addition rule in action when we do not have access to the raw frequencies. We can't count the number of cells of interest. So you need to use this version of the formula when you do not have access to the frequencies. It works with frequencies too, but the other formula that I showed you is a lot easier to use when you have access to the frequencies. So you got to keep in mind, you still do not want to double count those events that include both criteria. So you subtract the joint probability, this piece, right? The probability, the occurrence of both events, to avoid double counting the events in the middle of that Venn diagram. So that's why that formula works the way it does. So based on personnel records, you know that 30% of employees use 5 or more sick days per year, 10% of employees use 5 or more personal days per year, and 5% of employees use 5 or more sick days per year and 5 or more personal days per year. We want to know what percent of employees use 5 or more personal days per year or 5 or more sick days per year. So we know we're doing the addition rule. We see or, and we know it's 2 events because we're looking at 2 separate things. Sick days or not, right? That's one variable. And then personal days or not is another variable. So if we look at this, you'll see that you take the probability of 5 or more sick days, right? The first event. So that comes from here. 30% use 5 or more sick days. And there's that. This should have a point in it. And then the probability, because we're summing, right? So you add the probability of the next event, which would be using sick days. We know that 10% of employees use 5 or more, personal days. That's the next one, right? So you're adding, summing the probability of those 2 events, the separate probability of those 2 events together. Then you're subtracting the probability or the proportion of employees who do both things. So that comes from here, right? 5% of employees use 5 or more sick days per year and 5 or more personal days. So that's that co-occurrence piece right here. So you subtract that. 0.30 plus 0.10 is 0.40. 0.40 minus 0.05 is 0.35. So now you know 35% of employees have 5 or more sick days with an excused, 5 or more days with an excused absence, right? So 5 or more days taking a personal or a sick day, either one. You'll see that right there, right? So I'm just lumping personal or sick day into excused absence. So again, sum the probabilities for each individual event and then subtract the probability that those things co-occur. So now I want you to give this a try on your own. So take a look at this example problem and see if you can figure out which probabilities to add and then which one to subtract. All right, So now we want to look at this problem. So we know that we don't have access to the raw data, but we know that in the past month, 20% of patients were in critical condition. Whoa. 7% came in a helicopter, and 5% were both. There's your co-occurrence, right? So to figure this out, we're going to take the probability of critical condition, turn it into a p-value, plus the probability of helicopter, right, that 0.7, or 0.07 rather, be careful, minus that probability or percentage that both happen, the co-occurrence, critical and helicopter, that 5%. So 0.20 plus 0.07 minus 0.05 gives you 0.22. So there's a 22% chance that someone will show up in critical condition or in a helicopter based on this data right here. All right, so now we're moving on to even more practically applicable and common types of probability in the business world, where we're looking at two events that rely on one another, or that are dependent on one another, or that could or certainly do co-occur. So we're focusing on the multiplication rule for dependent events when two things could co-occur, or whether they do co-occur. And then we're looking at the conditional probability of any two events, where not only do they co-occur, but we have one thing that happened first. We're being very specific about a prerequisite, something that had to happen first before we look at the probability of something happening afterwards. So real quick, let's take a look at a visualization of dependent versus conditional. Now keep in mind, and we'll get into this later, dependent is a situation where you have and there's two separate events. And conditional is a situation where you have kind of a when situation. Does this happen when this already happened? So we're looking at the two different samples here. Well, actually, they're the same sample. But we're going to look at it in two different scenarios. So we're looking at dependent, the co-occurrence of two events among all possible events. So let's say we want to know the probability that we would randomly select somebody from this sample who is happy and a man, right? They're happy and they're a man. Their mood and that particular sex are co-occurring. So it would look like this. Those guys right there, that's our happy men. And if we were looking at probability of happy and man from this sample, we would take those 6 divided by the total number of people that you see here. So 6 out of 25, or 24% of the sample, are happy and a man. Now, when you're looking at conditional probability, you're looking at the occurrence of one event after a prerequisite or a previous event has already been established or is already assumed. So if we change this to go from happy and man to happy when man, we are no longer considering these women. The prerequisite is now being a man. That's the first event. That's the previous event. So we're only looking within the men to see the proportion that are happy. So you'll see that right there, right? So we're still looking at those 6 happy men, but now we're only dividing by the total number of men, the number of people who meet that prerequisite, being a man. So when we look at the entire sample, 24% of the entire sample are happy and men. But when we just look at men, 46% of the men are happy. That second one is excluding women. We're not looking at them at all. So now let's look at this in a more practical example without the cute little people there to illustrate the concept. So if you have two variables that occur simultaneously, not two events, but two different variables with events, so like one type of condition and one type of method of arrival, for instance, and they're occurring simultaneously, they definitely co-occur. Not they can co-occur, but you want to know how likely it is that they do co-occur, and you see the word and. That means both conditions must be met. It's not or, one or the other. Both things have to happen. Then you're definitely dealing with the multiplication rule for dependent events. Now keep in mind, if you look at this formula, it's the same formula as the addition rule for any two non-exclusive events. But in this case, there's only going to be one cell of interest in the table, that intersection, where the events actually co-occur. Okay, so before it was just the sum of cells of interest. Now it's where those two events co-occur. So let's take a look at this data. Let's say you want to know how likely that somebody would be in serious condition and walk in, right? They should not be walking in if they're in serious condition. It's very concerning. So you want to know how likely that is to happen based on how much it's happened in this data. So in this case, you don't care about the whole Venn diagram. You only want that intersection. Walk-in and serious are happening at the same time. So now you're just going to focus on the intersection where those two things occur together, and you're going to take that and divide by the total number of observations. So you've got 12 divided by 197 equals 0.061. Or based on this data, there's a 6.1% chance that someone who's in serious condition is going to walk in. Probably not a good idea. So now I want you to give this a try on your own to figure out the probability based on this data that any given patient is in good condition and will walk in. Just based on common sense, we think that's probably going to be more likely than if they're in critical, but let's use the data to figure it out. All right, so now we're looking for good here and walk in here. There's your intersection, right? So the number of cells of interest within the cells of interest where the two events co-occur is 90. And we're looking at the total number of observations yet again, which that's going to change for conditional probability. But for now, 197 is still our denominator. And we've got 90 divided by 197 is 0.457. So in this data, 45.7% were in good condition and walked in. And based on that, we think that there's a 45.7% chance that any given patient who will be in good condition and will walk in out of all the patients. So now let's take a look at the formula that you should use if you don't have access to the joint frequency distribution table, or in other words, the raw data, but you know the probabilities. Now we're going to focus on this. Now, this would work in the frequency distribution table as well, but it's less easy to use. It's easier to use in this case right here. So let's say, based on past experience, you know there's a 3% chance that a terminated employee will try to sue the company for wrongful termination, and a 55% chance that any employee will be terminated. What's the percent chance that any given employee will be terminated and file a lawsuit for wrongful termination? All right, so if we look at this, now we have to take the probability that they'll be terminated in the first place, and then multiply it by the probability that once they're terminated, they will sue. So the first event multiplied by the second event once the first event already happened, which as you'll find out in a minute, is the same as conditional probability. But we'll get there. So to do this, you know that there's a 55% chance that they'll be terminated in the first place, and then a 3% chance that once they're terminated, they'll sue. So you just multiply those two things together here, 0.55, which is the p-value for 55%, times 0.03, which is the p-value for 3%, you get 0.017. There's only a 1% chance that out of all employees, they'll be terminated and they will sue. Notice that within those who are terminated, 3% sue, but it's less likely that they're going to meet both criteria, right? That they're not only going to get terminated, but then they'll also sue. So now take a look at a slightly different example where we're looking at a 1% chance that a terminated employee will send a threatening letter to the manager, and then that same 55% chance that any given employee will be terminated. So how likely would it be that an employee would be terminated and send that threatening letter? It's funny, they're more likely to sue than be sending threatening letters. They jump straight to trying to get money. All right, so you take the probability of the first event being terminated, and then you multiply it by the probability that once they're terminated, they will sue, or the second event, that once they're terminated, they'll send a letter. So the probability of sending a letter when we already know they've been fired or terminated. Turn that percentage into a p-value equals 0.006, or a 0.6% chance that any given employee will be terminated and will send a threatening letter to the manager. So now let's get into the conditional probability of two events. So instead of, for instance, looking at the probability that they will be terminated and send a threatening letter, you could just look at within those who are terminated, how likely it is they would send a threatening letter, where we have a prerequisite happening. So we're no longer simply looking for the intersection of the two events or the co-occurrence. Now we're assuming the probability of the prerequisite, and you must include that in the calculation for the overall probability. So when you see this, we're looking at the first event, the second event, which is conditional upon the first event, and the order of events matters. Something happened when something else already happened. You have to be really careful with that. You'll see the formula here. We see the marginal frequency for the first event. So that's basically the total number of occurrences for the prerequisite. If you're using probabilities and not raw data, then you're focused on p-values and not frequencies. But it's basically doing the same thing. So if you have two variables that occur simultaneously and you see the word when, y depends on x, and we assume x already happened, you're probably dealing with the conditional probability of any two events. Again, this is just like the joint relative to group total when you have access to the frequency. So if you remember doing that back when we did frequency distributions and you calculated the percentage based on specific groups, that's what we're doing here, and that's what you'll see in the Excel assignment as well. So here's our data again with the methods of arrival and the different conditions that people arrived in. And we're going to be using this version of the formula because we're working with raw data. And again, marginal frequencies just represent the totals. All right, so suppose that the hospital administrator is interested in estimating the overuse of ambulances, and we need to know the probability that the next ER patient will come in an ambulance when they're in good condition and really don't need an ambulance after all. So the when, the prerequisite, is what comes after the line in this notation. So when we say what proportion or probability of patients in good condition arrive in an ambulance, another way to say that is the probability that they'll arrive in an ambulance when, the line's kind of like a when, they are in good condition. So ambulance when good. Because in this case, our prerequisite is that they're in good condition already. That's the first thing that's happened. So the joint frequency, the co-occurrence of good and ambulance, is right here. And we're not dividing that by 197 anymore. We're not looking out of all patients. We're looking just out of those in good condition. Just those 98 in good condition. So we've got 7 divided by 98 is 0.071. Now, what if we wanted to flip this a little bit? So what if the question was rephrased as, what proportion of patients who arrive in an ambulance are in good condition? Well, now we're saying good when they arrive in an ambulance, right? Patients who arrive in an ambulance, we're just looking at those patients. Now we're wanting to see how likely, once they've arrived in an ambulance, that they're in good condition. Maybe the people who deal with ambulance arrivals want to know what they're in for based on, probabilities. So if we look at this, we're still looking at that same joint frequency. We're still looking at good and ambulance. But now we're only interested out of those who arrive in an ambulance, these 61, what proportion are in good condition? So you see that here now, right? 7 divided by 61, 0.115. So whatever comes after the word when, if you rephrase it with the when, that is going to be the first event that you want to look at the marginal frequency or the total for. So now I want you to give this a try on your own. I was nice and I kind of gave you this version of the formula because that helps you figure out what's the prerequisite. But take a look at this and see if you can figure it out on your own. Pause the video and try it. All right, so now let's say that a hospital administrator is concerned with the wait time for walk-ins and wants to estimate how many patients are at risk because they're in serious condition of perishing in the waiting room. So we want to estimate the probability that the next ER patient will walk in when they are in serious condition. Another way to say this is what proportion of people in serious condition will walk in. So our prerequisite is that they're in serious condition, and we're worried about them. They're in serious condition. You shouldn't be walking in. So we look at the intersection of walk-in and serious. That 12 right there. Now remember, we're only concerned with the people in serious condition when they're in serious condition. So we're only looking at these 35 people, right? So in the picture that we saw at the beginning of this section, when we were looking at being happy when a man, we only looked at the men, right? We didn't look at the women. So now we're not looking at anybody in these conditions. We're just looking at serious condition. We're ignoring the total frequency or the frequency of all occurrences. So this leads us to 12 divided by 35. So out of all the people in serious condition, 12 walked in, which is a probability or proportion of 0.343. So based on this data, the hospital administrator should worry that 34.3% of patients in serious condition will walk in. So now let's take a look at a situation where we have no access to the joint frequency distribution table, but we know the probabilities, and we're going to focus on this formula. So based on personnel data, you know that 20% of employees had no missed days and scored high on their performance appraisal last quarter. And among those with no missed days, 36.4% had high performance. You also know that 55% of employees had no missed days last quarter. So this question is asking what percentage of employees had high performance when they had missed no days. So we know that out of everybody, 20% had no missed days and scored high on their performance appraisal. Here we know that just out of those who had no missed days, here's the percentage that had a high performance appraisal, and here's how many employees had no missed days in general. So if we're looking at the probability of the co-occurrence of both events, so no missed days and scored high on their performance appraisal, that's this 0.20 based on the 20%. If we're looking at the probability of the occurrence of the first event, so the first event would be missing no days, right? Because we're looking at when they miss no days. So the probability or the percentage of employees that had no missed days was 55. So the P version of that is right here, and you get 0.364. Now notice that the answer is actually already in the question, right? Because if we look at this right here, that is among those with no missed days, they met the prerequisite, 36.4% had high performance. So the conditional probability was actually in the problem, but you still can use the math to calculate it based on the other values. So now let's take a look at a conditional probability example that I want you to try on your own using the probability version of the formula. So pause the video and give it a shot. Okay, so for this one, I only gave you two probabilities. I didn't give you a third one, or the answer, actually. But this makes it pretty simple. There's only two to work with. You just have to figure out which one is for the co-occurrence and which one is for the occurrence of the first event. So we want to know the probability that someone will walk in when they're in serious condition. Or if someone's in serious condition, what's the probability that they will walk in? So you don't only see the when there, but it's implied, depending on how you state it. So we know that the probability of patients walking in serious condition was 0.075. Another way to say that would be walking in and in serious condition. So that's going to be our co-occurrence, both these events happening at the same time. So now we know that it's that 0.075, that's our numerator. Then we look here to find the probability of the occurrence of the first event being in serious condition, and we know that 0.30 or 30% of patients are in serious condition. They met that prerequisite, put that there, and you end up with 0.25 or 25% chance that a patient will walk in when they are in serious condition. Whew, we're done with examples. Now keep in mind that probability is a key way to improve business decisions, and it allows you to determine the likelihood of many business relevant outcomes, including like customer behaviors like purchasing and like complaints, or employee behaviors like quitting and improving performance based on training. It allows you to make predictions about defects in parts or the success of new initiatives like training and expansion. However, your predictions are only as good as the source of your data. So make sure if you're ever trying to use this kind of probability, you want to have a large sample that represents the population. So you want to have many, many observations over a time period that's relevant to what you're trying to make predictions for and that are relevant to the outcomes of interest. So now that we've gone through a ton of examples, we've looked at some math, I'm just going to give you the highlights of this lecture so that when you're looking at this on your own, you'll be able to quickly go to which rule is most appropriate. So here's your summary of the formulas and selecting which rule to use. If we have a situation where you see or, you know you're working with an addition rule, right? Here's another or, there's another addition rule. If you're working with a situation where you see and, you're working with a multiplication rule. Now, if you see or, and you're just looking at a single variable, so 2 different methods of arrival, or 3 different methods of arrival for that matter, or different conditions, or different sexes, or different things within a single categorization, single variable, you're doing the addition rule for individual outcomes. And remember, you have 2 different versions of the formula, one when you're working with the table, one when you're working with a summary of the probabilities. Next one, if you see and you're still working with the single variable, right? Something happens and then something else happens, looking at the same variable, you're using the multiplication rule for independent events. And you'll see here, you're basically multiplying all the probabilities together, right? These are just fancy ways to find the probabilities. With the addition rule, you're summing, you're adding things up, right? You're adding here or you're adding here if you're using probabilities. Here you're multiplying, hence multiplication rule. Now, if you have 2 variables, but you see the word or, right? Whereas here we have 2 variables, it's 1 variable we see or. Here we have 2 variables, we see the word or. You're using the addition rule for any 2 non-exclusive events. So this is a situation where 2 variables could co-occur, but they don't necessarily have to look at that probability. So arriving to the hospital in a helicopter or in good condition, right? We've got arrival method, we've got condition, and we've got an or situation. So here, remember, you want to just count the numbers in the cells of the rows of interest without double counting, or if you're using a story problem, you add up all the probabilities for each event individually and then subtract the co-occurrence of those things happening together. Now finally, we're looking at our co-occurrence or our prerequisite types of probabilities. So the multiplication rule for dependent events, just like the other multiplication rule, you see the word and, or at least the and would apply if you restated it. You've got 2 variables that definitely do co-occur. Not that just they could, but they do co-occur. And one thing happens and another thing happens. And we're looking at 2 variables here. So arriving to the hospital in a helicopter and being in good condition. Here you're focusing on the intersection. You're adding up. You don't really have to add up very much. It's really just the number within that cell where those 2 things are happening, assuming you're looking at 2 events. And the total number of observations is here. Or you could use the probability version of the formula with the story problem, where you take the probability of the first event and multiply it by the probability of the second event when the first event already happened. So this is your prerequisite, and then this is your conditional probability that you see right here. So conditional probability is specific. It's not just these things co-occurred, but something happened first. So after we already know something happened, how likely is it that something else was going to happen? So this is the only one where it's kind of a win situation. And it's when you have 2 variables where one event precedes the other. So arrives to the hospital in a helicopter when in good condition. Or in other words, among those who are in good condition, how likely is it they'll arrive in a helicopter? We're just looking at a specific subset of that sample. So with the raw data, you look at the total for the total number of outcomes for the first event, the prerequisite, and you look at where those 2 things co-occur. For the probabilities, you look at the probability of the co-occurrence and divide by the probability of the prerequisite, or the whatever happened first, something, 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 when prerequisite happened. So I hope this summary is helpful because I gave you a ton of information in this lecture, and you will be expected to figure out which rules are appropriate in the real world and maybe in some of your assignments as well. So hopefully this summary will be beneficial to you, not only in the class, but if you ever have to do this on your own and you're struggling to figure out which rule and which math to use, these two slides should be very useful.